Greetings to you. We will begin our next session on electrochemical methods. In the last class we had seen electrogravimetric analysis a little bit, and then we had defined several terms, that is Ohm's law and other things. What we had I had told you is regarding the electrogravimetric method, they especially it deals with the deposition of the element electrolytically from upon a suitable electrode. So, filtration is thus avoided and some co-deposition and other related methods, related problems with respect to normal gravimetry, they have been avoided. And then we also saw a little bit of Ohm's law. After the Ohm's law, we saw this electrolytic cell regarding cathode, and then we looked at what is an anode, what is a cathode, and what are the polarized electrodes, etc. And then we had looked at over voltage, decomposition potential, and all these definitions I had passed on to you. And then I had told you that electrodes can be made of all these platinum or platinum iridium gauges, etc. And determination of copper, lead, cadmium, nickel, many of the metals can be carried out routinely. Now we will go to the next technique, that is of electrochemical methods, that is conductometric measurements. So, what is conductometry? Conductometry is nothing but the measurement of conductance, that is current. So, conductometry is used in direct and indirect methods of analysis. For example, complexometry, chemical kinetics, precipitation titrations, wherever there are ions involved and there is an appearance or disappearance of the ions, we can use conductance analysis. So, in complexometry, normally ions will complex and then they will become neutral, charged or uncharged species. In chemical kinetics, ions may be consumed or added in the chemical reactions. So, it can be used for chemical kinetics. In precipitation, definitely the precipitate is supposed to be neutral and ions will be removed. So, like that there are wherever there is appearance or disappearance of ions, conductometry can be used. So, conductometric analysis is based on the measurement of the electrical conductivity of the solution, that is directly entirely due to the movement of cations and anions. So, the charge transport involves both these processes while simultaneously maintaining electrical charge that depends on the mobility of the ion. So, different ions move towards cathode or anode at their own speed. It is like running race where there are several participants. All the cations will be moving towards the cathode and all the anions will be moving towards the anode. So, the mobility of the cations and anions are not only the specific property of the ion, but it also depends upon several factors. For example, the mobility is affected by the charge, whether it is monovalent, divalent, trivalent, etc., or it can then it depends on the size of the ion. If the ion is very small, then it will move very fast. If the size is bigger, then it will move rather a little sluggishly, and then it depends upon the mass and the extent of solvation. So, what is solvation? Solvation is nothing but the water molecules surrounding the ion. For example, if I can draw hydrogen ion. This is the hydrogen ion, and then the water is nothing but oxygen, hydrogen and hydrogen. The ions are electrons are 2 electrons are here, they are attracted to the towards H plus. So, each hydrogen ion would be surrounded by number of solvent molecules like this, water molecules here. And then I can write here one more and hydrogen, another hydrogen, so many water molecules I can write. So, these water molecules are usually associated with the cation. Similarly, anion also. Why? Because OH minus ions would be attracting H plus ions around it. If I have OH minus ions, then there will be H plus ions would be surrounding it all around. So, in general, the H plus, where do the H plus part come from? It comes from the water. So, the so if I have a water molecule like this with oxygen at the apex, hydrogen at the bottom like this, with hydrogen ion, oxygen will be attaching all around the hydrogen, and with OH minus ions, hydrogen atoms of the water molecule will be attached around it. So, the orientation will be something like this. This is not correct. So, this is H plus, yeah, another H plus, this is OH. So, H2O molecules will be going around it. So, there is water of extra lot of solvation of the ions. So, the mobility is defined as the rate of the movement of the ion through the solution under the influence of an electric field or a concentration gradient. So, we also have a concentration gradient, that means any ion moving around towards an cathode or anode would be having competition from other ions present in the same solution. So, sometimes what happens, all the cations will be moving towards the cathode and all the anions will be moving towards the anode under the influence of electric field. So, there will be some competition among the cations to reach the cathode. So, we call it flux. So, there will be some concentration gradient will be built up over a period of time and space near the cathode. So, the ions have to move through that gradient, concentration gradient. So, the difference in the rates of diffusion of the ions gives rise to liquid junction potential. So, there are a lot of things are to be said towards liquid junction potential. It is a highly researched area among the electrochemical scientists, and we will talk about it as and when the time permits or at the appropriate time. For the time being, it would be nice if you understand that there will be some sort of competition for the cation to reach the cathode under the influence of other cations and solvent molecules, because all cations have to pass through the solvent media to reach the cathode. Okay. So, conductance, in the case of electrolytes, the term we define a term called as conductance, that is C, that is used generally. It implies the ease with which the current flows through a conductor. Thus, the conductance is the reciprocal of resistance. What is resistance? Resistance is the opposition for movement of the electrons and conductance is the ease of the movement of the electrons. So, obviously conductance is the reciprocal of the resistance. So, I can write mathematically something like this, that is C is equal to 1 over R. So, C is equal to 1 over R, where C is the concentration and R is the resistance. So, it is expressed in units of reciprocal ohms or mhos. Okay. So, if there is resistance, then we also can define what is called as specific resistance. The resistance R of a conductor is directly proportional to its length and inversely proportional to its area of cross section. Okay. So, what we are talking about here is we are talking about a wire which is essentially a conductor of electrons, okay, that is a solid, and the resistance, any solid substance metal will offer resistance for whether it is metal or non-metal, either way. If it is a solid or liquid or something like that, a wire will offer resistance. Because of the resistance, it gets heated also. That is another aspect which is part of the phenomenon which everybody knows, that we heat water with our electrical coils. So, there it gets heated because of the resistance. So, the resistance of a conductor is directly proportional to its actual length as well as cross section. How much of the volume is available for resisting the conductance. So, it is inversely proportional to its area of cross section. So, we write R is proportional to L and R is proportional to area, inversely proportional. So, R, we can remove the proportionality constant and write R is equal to rho into L by A, where rho is a constant called as specific resistance, which should be typical, a characteristic of all the elements which can conduct electricity. So, for elements like copper and gold, silver, etc., specific resistance will be very less. For other metals, it will be higher than that. So, a specific resistance is also called as resistivity, and if length is 1 centimeter and area is 1 centimeter, then rho R becomes O. This is 1, this is 1, denominator and the numerator. If both of them become 1, R should be equal to 1, rho, not 1. So, specific resistance is defined as the resistance of a uniform column of the material of the conductor having a length of 1 centimeter area of cross section and 1 square centimeter. We know that rho is equal to R into A by L, that is in ohms. So, specific resistance is expressed as ohms per centimeter inverse, that is the unit for ohms. So, then we can define what is known as specific conductance. The specific conductance of any conductor is the reciprocal of the specific resistance. It is very simple. We know what is resistance, and inverse of resistance is nothing but the specific conductance. So, how do we determine the denote the conductance? Unit is K. So, we write K is equal to 1 over resistance into L by A, that is length divided by area, that is ohms inverse, centimeters inverse should be the units for the conductance. So, if again as usual, if L is equal to 1 and A is equal to 1, K should be equal to 1 over R, that is rho. Specific conductance can be defined as the conductivity offered by a solution of by length 1 centimeter and area of 1 centimeter cross section. It is expressed in not in ohms, but in mhos. Okay. This is a very convenient term instead we write reverse of ohms is mhos. So, just to indicate that conductance is the reverse of resistance. So, mhos per centimeter is the unit for conductance. So, we may also define what is the conductance of a solution containing 1 gram equivalent of the electrolyte. So, now what I taught you about the basic concepts of chemistry will become very useful, because I am going to talk about many of those technical terms now. So, 1 gram equivalent of any salt, if I dissolve, that is called as electrolyte, when placed between two sufficiently large electrodes which are 1 centimeter apart. 1 centimeter apart they should be, and in between there should be solution. So, the specific equivalent conductance is denoted by lambda V, where V is the volume in milliliters containing 1 gram equivalent of the electrolyte dissolved in that, and it is measured in reciprocal ohms or mhos. Okay. Then I can also define what is known as molecular conductance. This is defined as the conductance of a solution containing 1 gram mole of the electrolyte when placed between two sufficiently large electrodes placed 1 centimeter apart. So, that is molar conductance, that is denoted by mu V, and it is measured in mhos. So, we can derive some sort of a relationship between the specific conductance and equivalent conductance, and if the solution containing 1 gram equivalent of the electrolyte is dissolved in VmL of the solution, then lambda should be equal to K into V. So, equivalent conductance should be equal to specific conductance into volume of the solution in ml containing 1 gram equivalent of the electrolyte. These are all basic definitions, nothing to we are not deriving any equation yet. So, only the thing required of you is to understand how we are defining each and every parameter. So, this is the relationship between molecular conductance and specific conductance. So, here it is quite similar to the equivalent conductance and specific conductance. We write mu V is equal to K into V, or in words, if I have to describe what is molecular conductance, it is nothing but specific conductance multiplied by the volume of the solution in milliliters containing 1 gram mole of the substance, that is molar conductance. Then we also have to think about the effect of dilution on the conductance. So, it is expected that the conductance of a solution should increase on dilution. This is understandable now. For example, if you take water, pure water, then what happens? I have only pure water and very few ions. What is the number of ions in water? Pure water contains 10 raised to minus 7 moles, 10 raised to minus 7 H plus ions, and 10 raised to minus 7 of anions. In 1 gram equivalent there should be 18 molecule. In 18 grams that will be concentration of cations and anions will be 10 raised to 14 minus 14. So, if the solution is very pure, there are not many ions. So, I put only one small ion, and then that can move very freely. So, the effect of conductance normally on the specific conductance is expected that specific conductance should decrease on dilution, and on the equivalent and molecular conductance the equivalent conductance will increase on dilution. Similarly, molecular conductance also will increase on dilution. So, the variation of the equivalent conductance with dilution we are showing here in this figure. So, you can see this is the conductance, this is the concentration. So, if I have a weak electrolyte like acetic acid, the equivalent conductance will keep on coming down, and then if it is a strong electrolyte, then it will be very predictable upon dilution, but near the very dilute solutions it will be increasing much faster. At higher concentrations it will be almost predictable, linear, but increase the concentration, decrease the concentration more and more, the electrons will be, the ions will be able to move faster. So, a strong electrolyte like potassium chloride, that will increase the conductance. So, the maximum value of the equivalent conductance of an electrolyte obtained at very high dilution is called as the equivalent conductance at infinite dilution. So, how much it can increase, basically that is what we are looking at. So, at infinite dilution, whatever is the conductance you get, that would be the equivalent conductance of the electrolyte. So, by infinite dilution, what do we mean by infinite dilution? We cannot have infinite dilution, it does not mean anything. Okay. So, what we exactly mean is that the solution is already so dilute that further dilution will not produce any change in the equivalent conductance. This is how practical definition of an infinite dilution comes about. It is the dilution after which the equivalent conductance will not increase if you dilute it more. That is almost infinite dilution. Okay. So, here is a table for you to understand what is equivalent conductance at infinite dilution, that we denote it by lambda infinity here, it is here. Okay, lambda infinity. The equivalent conductance of ions at infinite dilution are always measured at particular temperature. So, we write 25 degree centigrade here. This is only useful for comparison. So, what do we have here? H plus, what is the equivalent conductance? 349.8, and OH minus is approximately half of that, 198.6. Okay. Then lithium is 39, fluoride is 55, sodium is 50, chloride is 76.35. The first column is cation, then equivalent conductance, then anion, then we have the equivalent conductance for anions. You can see that there is not much difference between the equivalent conductance of ions, whether it is anion or cation, except for this H plus and OH minus. So, if all acidic solutions containing H plus will show very high equivalent conductance, and alkaline solutions also will show high, but it will not be as much as acidic solutions. Equivalent conductance will be approximately half of that, maybe slightly half, less than half, but all other things are known to the plus or minus 1 unit. Okay, that is 39, sodium is 50, calcium is 60, barium is 64, CO3 is 69, all within that range, less than 100. Very few are there above 100 except hydrogen and hydroxyl ions. So, the conductance of a solution, if it contains many ions, then how do we explain, how do we write, express? So, what we do is the conductance is nothing but 1 over resistance, that we know. So, it is the product of C1 lambda 1, that is ions. Okay. So, ions and equivalent conductance of the first ion, second ion, third ion, fourth ion, nth ion. So, the Ci terms are the concentrations of various ions in solution, C1, C2, C3, etc. And lambda 1, lambda 2, lambda 3 are the numerical constants of the characteristics of the ions, and x is the proportionality factor that takes into account the geometry of the cell. That is very important. So, geometry of the cell is dependent upon how we are constructing our measurement unit, our electrochemical cell, whether they are exactly 1 centimeter apart, whether they are exactly 1 square centimeter cell or 5 square centimeter cell, etc. Calculation part will come later. So, the conductance of a solution can be measured by finding out the resistance. How do we do that? We do it with Wheatstone bridge arrangement, and some of the conductance bridges are I am showing you here. This is known as Kohlrausch conductance bridge. Here I have a wire, and then this is the wire A to B, and then I have a resistance. So, 1 and 2, here the bridge circuit. So, here the bridge is completed. If this is the simplest bridge which is used for the measurement of conductance of different solutions. It consists of a mere 1 meter bridge wire. This is AB with a fixed resistance, that for any metal wire the resistance is fixed, okay, and that wire is fixed at both ends to increase the effective length of the wire, and it has got a resistance box R. This is our resistance box. I can increase or decrease the resistance, and then a conductance cell, that is C. This is our conductance cell, okay, with 2 electrodes separated. That is how normally a cell is drawn, represented, and it has got a head D here and a small induction coil I, which is operated by means of a battery. This is a simple conductance bridge. So, what is a conductivity cell? The solution whose conductivity is to be measured is taken in a cell called as conductivity cell. Different types of conductivity cells are used for different purposes. However, the fundamental requirement is for having a pair of electrodes that are firmly located and connected to wires outside in a fixed geometry. It can be square or triangle or circular or whatever it is, and with respect to one another. And the 3 types of cells which are generally used are shown here. You can see here I have a single wire here, another wire here in a beaker connected to wire outside. This will lead to Wheatstone bridge. So, this is one type. Here I have another type, an electrode made of a made into a thin sheet like this, and then here I have the electrode made into circular shape or any other shape and connected with a salt bridge. Okay. So, different types of conductance are there, A, B, C, and now we talk about the electrodes used in conductivity measurements. We have here the electrodes are generally made of 2 parallel plates of platinum foil. What is a foil? Foil is a squarish plate. You have heard of aluminum foils. So, in the supermarket, etc., if you go, they will pack your food or whatever you buy into an aluminum foil. Similarly, platinum foils are available, it will not be so thin, but it will be slightly thicker, and so that they do not bend easily. So, the relative positions of these electrodes are fixed by sealing the connecting tubes that we have already seen in the previous slide into the side of the conductivity cell. Here you have seen. So, they are all bound at the back. Although alternating current is employed to remove the polarization, yet it may occur to some extent. Polarization cannot be avoided completely when smooth platinum electrodes are used. So, in order to reduce the polarization, the electrodes are coated with finely divided platinum black powder. Okay. So, what we have as electrodes are basically two platinum foils coated with platinum powder, black platinum powder. So, platinization, how do I do that job? That process is known as platinization, and platinization is carried out by taking 2 or 3% of the solution of chloroplatinic acid and 0.02 to 0.03 gram, that is approximately 30 milligram. 30 milligram of lead acetate in the cell. The amount of the solution should be enough just to dip the electrodes. Okay, I take a solution of chloroplatinic acid and add a little bit of lead into that, lead acetate, and current will be passed for about 15 to 20 minutes. The electrolysis of the chloroplatinic acid will take place. So, what it will produce? H plus and chloroplatinic anion. So, okay. So, the electrode anions will move towards the anode and cations will move towards the cathode. So, platinum ions will move towards the cathode, that is on the platinum foil, they get deposited as a black powder. So, that is how we prepare them. Then we can wash the electrodes repeatedly with distilled water and finally with conductivity water. When not in use, these should be kept in conductivity water. What is a conductivity water? It is a water with minimum conductance. So, what is conductivity water? It should be of very high purity, that means it has no conductance due to dissolved impurities, only pure water. For this reason, ordinary water is not suitable. You cannot store a conductance electrode in normal tap water or well water or sea water or any of the waters. So, because it may contain dissolved CO2. Apart from the salts, it should not have CO2 also. Why? Think about it. I will give you 2 seconds. CO2 should not be there in the water where we store the conductivity electrodes. Okay. The reason is CO2 will dissolve in water producing carbonic acid, that is HCO3, H2CO3, which can ionize as H plus and HCO3 minus ions. So, again there is conductance is introduced. So, for most purposes conductivity water is used in conductance measurements without dissolved carbon dioxide. It can be prepared by distilling water containing small amounts of sodium hydroxide and potassium permanganate. You take water, add a little bit of potassium permanganate, a drop of sodium hydroxide, distill it, whatever you collect would be approximately conductivity water. Okay. So, to conduct conductivity experiments, we need a source of conductance, AC. So, this source of AC consists of a double mercury arc arrangement capable of giving a symmetrical sine wave of AC of constant frequency. Hall and Adams in 1919 suggested a vacuum tube oscillator for conductivity measurements. The essential circuit is shown here. So, very simple circuit. These are all connect coils and vacuum tube. This is known as vacuum tube oscillator if you have all these electrical units. So, the grid circuit of the vacuum tube contains a grid coil L1 I have written here. Okay. There is one L1, L2, L3, these are all grid coils. So, that is in parallelly connected to the variable condenser C. The coil L3, which is an output of coil, is coupled with L2 inductively and conveys the oscillations to the conductance bridge. So, the vacuum tube oscillator is better than other oscillators because it is silent in operation and gives alternating current of constant frequency. So, such units you do not have to struggle to make it, they are available across the shelf in the scientific shops. All you have to do is go and say you want a AC source supply. I am only teaching you the principle of that. We will continue our class with the determination of conductance measurement in the next class and see how we can apply it towards the chemical analysis. And at this stage I can only tell you that a conductance unit, conductance measurement is part and parcel of every laboratory worth its name in pollution control. Thank you.